Look up at the night sky. What do you see? A scattering of stars, maybe the hazy band of the Milky Way. But what if I told you that every single one of those pinpricks of light is part of an unimaginably vast cosmic story? A story that began billions of years ago and is still unfolding right now. Galaxies, those swirling cities of stars, aren't just static decorations in the darkness. They're alive, evolving, colliding, and birthing new generations of stars in a dance that stretches across the ages. And here's something that might blow your mind. The light from some of those galaxies has traveled for so long that by the time it reaches your eyes, the galaxy itself might already be gone. This is the grand drama of galaxy formation and evolution, a tale written in stardust and gravity. Think about it, every galaxy, from the smallest dwarf to the largest supergiant, holds secrets about how our universe grew up. How did these cosmic titans take shape from the formless fog of the early universe? What forces sculpted their spiraling arms or flattened them into smooth ellipses? And what happens when two galaxies crash into each other in a collision so slow and majestic it makes geological time look like a blink? The answers aren't just fascinating, they're humbling. Because when we study galaxies, we're really studying our own origins. Every atom in your body was once part of a star, and every star was born in a galaxy like these. That's why today we're going on a journey through 30 astonishing facts about how galaxies form, change, and sometimes even die. We'll uncover how dark matter, the universe's invisible scaffolding, shapes their growth, why some galaxies are cannibals that devour their neighbors, and how supermassive black holes at their hearts can ignite or extinguish entire generations of stars. This isn't just a list of facts, it's a backstage pass to the greatest show in the cosmos. So let's dive in, because the story of galaxies is, in the end, the story of us all. It might seem impossible, but those glittering galaxies we admire are actually deserts of nothingness. Picture this: if you shrunk our entire Milky Way galaxy down to the size of a football field, each star would be no bigger than a grain of sand. And here's the kicker: those grains would be scattered miles apart from each other. That's how much empty space fills a galaxy. The distances are so vast that even with hundreds of billions of stars packed into a single galaxy, the chance of two randomly colliding is almost zero. Think about our closest stellar neighbor, Proxima Centauri. It sits 4.2 light-years away, so far that if you drove a car at highway speeds non-stop, it would take you 48 million years to get there. And yet, that's considered a stone's throw in galactic terms. This emptiness isn't a fluke, it's a rule. Gravity sculpts galaxies by pulling stars into loose clusters and sweeping arms, but it leaves oceans of darkness between them. Even in the densest parts of a galaxy, like the core of a spiral or a globular cluster, stars still orbit with vast breathing room. Imagine throwing a handful of marbles into an Olympic-sized swimming pool. That's the density of stars in most galactic neighborhoods. But why does this matter? Because this emptiness shapes everything. It means light from distant stars rarely gets blocked, allowing us to peer across billions of light years. It means planets can orbit their suns undisturbed for eons. And most strikingly, it means galaxies themselves can collide. Not in a fiery crash of stars, but in a slow-motion, ghostly dance where stars slide past each other like ships in the night. That emptiness is the canvas on which the universe paints its greatest masterpieces. Right now, as you gaze up at the stars, our galaxy is locked in a silent, slow-motion disaster, one so immense it defies human comprehension. The Milky Way and our nearest galactic neighbor, Andromeda, are hurtling toward each other at nearly 250,000 miles per hour. That's fast enough to circle Earth's equator 10 times in a single second. Yet despite that staggering speed, the collision won't happen for another 4.5 billion years. Why? Because space isn't just big, it's unfathomably big. The two galaxies are currently 2.5 million light-years apart, which means even at their breakneck pace, it'll take eons for gravity to pull them together. When that day finally comes, it won't be the fiery explosion you might expect. Galaxies are mostly empty space, remember, so instead of stars smashing together like billiard balls, they'll perform an extraordinary cosmic ballet. Picture two vast flocks of birds merging midair. Each star will weave gracefully past the others, pulled into new orbits by shifting tides of gravity. Over billions of years, the two galaxies will stretch, twist, and eventually settle into a single, colossal structure astronomers nicknamed Milkomeda. Computer simulations reveal something even more astonishing. As the galaxies merge, they're supermassive black holes. Each weighing billions of times the mass of our Sun will spiral toward each other, unleashing ripples in space-time called gravitational waves. The final act, a titanic black hole merger shaking the fabric of the universe itself. But here's the twist Earth probably won't notice. By then, our Sun will have swollen into a red giant, likely vaporizing our planet long before the galaxies finish their dance. Yet somewhere in that new hybrid galaxy, fresh stars will ignite, new planets will form, and the story of the cosmos will continue written in starlight and silence. Here's a cosmic mystery that will bend your mind. Galaxies spin so fast they should fly apart, but they don't. Stars at the outer edges whip around at speeds that defy the laws of gravity as we know them, as if some unseen hand is holding them together. That hand, dark matter, it's the universe's invisible architect, an enigmatic substance that doesn't emit, absorb, or reflect light, yet it outnumbers ordinary matter 5 to 1. Without it, galaxies as we know them wouldn't exist. Picture the early universe, a hot soup of particles just after the Big Bang. Tiny ripples of dark matter, colder and slower than regular matter, began clumping together first. These clumps acted like gravitational seeds, pulling in gas and dust over billions of years to form the galaxies we see today. Think of dark matter as the framework of a skyscraper hidden beneath the walls but holding everything upright. Without that framework, galaxies would lack the gravity needed to gather their stars into those majestic spirals and glowing orbs. Here's where it gets wild. Dark matter doesn't just build galaxies, it steers them. Astronomers studying galaxy rotation curves found something bizarre. Stars far from a galaxy's center orbit just as fast as those near the middle, like children on a merry-go-round, all spinning at the same speed no matter where they sit. That's impossible under Newton's laws unless there's extra mass we can't see. Dark matter forms an enormous, diffuse halo around each galaxy, its gravity gripping stars tight even in the outermost reaches. But how do we know it's there if we can't see it? The same way you know wind exists by watching its effects. Light bends around massive galaxy clusters in ways that betray the presence of unseen mass. Computer simulations of the universe match reality only when dark matter is included. Even the cosmic microwave background, the afterglow of the Big Bang, bears its fingerprint. So next time you look at a galaxy, remember, what you're seeing is just the glitter on the surface. The real story is written in the invisible. At the heart of nearly every galaxy, including our own Milky Way, lurks a monster so powerful it bends the laws of physics. Supermassive black holes, weighing millions to billions of times more than our Sun, are the invisible puppeteers of galactic evolution. Take Sagittarius A, the behemoth at our galaxy's core. Though it's 4 million times the Sun's mass, you could fit its event horizon inside Mercury's orbit with room to spare. Yet its influence stretches across 50,000 light-years, shaping the destiny of every star in its domain. How do these cosmic giants form? The leading theory is a story of relentless appetite. In the early universe, dense clouds of gas collapsed directly into black hole seeds, while others grew by devouring stars and merging with rivals. Over billions of years, they gorged themselves into supermassive status, but here's the twist: their growth isn't mindless destruction. These black holes are celestial regulators, their gravitational jaws acting like a cosmic thermostat. When they feed too greedily on surrounding gas, the infalling material heats up and blasts out radiation so intense it pushes away nearby star-forming clouds, effectively putting the brakes on new star birth. This feedback loop prevents galaxies from burning through their fuel too fast, stretching their stellar lifespans across eons. Yet sometimes these black holes flip the script entirely. In quasars, the brightest objects in the universe, supermassive black holes transform into cosmic lighthouses. As matter spirals inward at nearly light speed, friction heats it to millions of degrees, outshining entire galaxies. These outbursts can sterilize whole regions of space, halting star formation entirely, but they can also trigger it. Shock waves from black hole jets compress distant gas clouds, sparking new stellar nurseries far from the galactic core. It's a paradox. The same force that suppresses star birth in one place can ignite it in another. Our own Sagittarius is relatively quiet now, but evidence suggests it wasn't always so meek. Fossil X-ray glows reveal it likely flared up as a quasar 2 million years ago. Its blast so powerful it left scars on the Magellanic Stream, a river of gas trailing our galactic neighbors. Even today, it occasionally snacks on passing gas clouds or stars, producing flickers of X-rays visible across the galaxy. What's truly mind-bending? These black holes might be the reason galaxies exist at all. Simulations show that without their gravity anchors, early galaxies would have blown apart, their stars scattering into the void. So next time you peer toward the Milky Way center, remember, you're looking at the silent guardian of our galactic home, a reminder that even in the darkest corners of space, there's an invisible hand guiding the dance of the stars. Galaxies aren't just floating peacefully through space, they're ruthless cosmic predators. Behind those glittering spirals and serene elliptical shapes lies a brutal truth. Big galaxies grow by devouring smaller ones. It's called galactic cannibalism, and our very own Milky Way is guilty of it. Right now, it's in the process of tearing apart the Sagittarius dwarf galaxy, a tiny neighbor that's been orbiting us for billions of years. Gravity has stretched it into a looping stellar stream, wrapping around our galaxy like a strand of cosmic spaghetti. Here's how it works. When a small galaxy ventures too close to a larger one, the intense gravitational pull starts shredding it apart. Stars get yanked away, forming long, glowing tendrils called tidal streams. The Milky Way has left behind evidence of at least a dozen such meals. One of the most dramatic examples is the Gaia sausage, the remains of a dwarf galaxy that collided with us 8 to 10 billion years ago. Its stars didn't scatter randomly. They were flung into orbit so extreme that astronomers can still trace their paths today, like breadcrumbs leading back to a violent merger. But why does this happen? It all comes down to gravity's relentless tug. Larger galaxies have deeper gravitational wells, and once a smaller galaxy crosses a certain threshold, escape becomes impossible. The process isn't quick. It can take billions of years, with the victim galaxy getting stretched thinner and thinner until it's nothing but a ghostly smear of stars. The real kicker, these mergers aren't just destructive, they're creative. When galaxies collide, the chaos can compress gas clouds, triggering bursts of new star formation. The Milky Way's outer halo is littered with ancient clusters of stars that likely came from devoured galaxies, each one a fossil of a long-dead cosmic encounter. Even our Sun might owe its existence to one of these collisions, born from gas stirred up by a past merger, and the cycle continues. In 4 billion years, when the Milky Way and Andromeda finally collide, their merger will create an even larger galaxy, one built on the bones of countless smaller ones. It's a reminder that in the grand scheme of the universe, even galaxies aren't permanent. They're shaped by violence, rebirth, and an endless dance of consumption. Let's rewind the cosmic clock to a time when the universe was barely out of its infancy, just 400 million years after the Big Bang. That's when the light from galaxy GNZ11 began its journey toward us, making it the oldest and most distant galaxy ever observed. To put that into perspective, this ancient beacon existed when the universe was a mere 3% of its current age. Imagine catching a glimpse of a newborn's first breath. That's the scale of this discovery. What makes GNZ11 so extraordinary isn't just its age, but what it's telling us about the early universe. For decades, scientists assumed the first galaxies would be tiny, dim, and chaotic like celestial toddlers fumbling through their early stages. But GNZ11 shattered those expectations. Despite its youth, it's already massive, blazing with the light of 1 billion suns and forming stars 20 times faster than our Milky Way does today. It's as if we found a medieval cathedral built the day after the invention of the hammer. How did this galaxy grow so big, so fast? The answer might lie in the universe's primordial soup. In those early eons, space was smaller, denser, and packed with raw material. Gas clouds collapsed under their own gravity more easily, spawning colossal stars that lived fast and died young, seeding the cosmos with heavy elements. GNZ11's intense star formation suggests it feasted on these pristine resources, growing unchecked in a universe without competition. But here's the real puzzle. GNZ11 shouldn't be visible to us at all. The early universe was fogged with neutral hydrogen, a cosmic haze that should have blocked its light. The fact that we can see it hints at a pivotal moment, the epoch when the first stars and galaxies ionized this fog, burning away the mist and carving the first clear windows into space. GNZ11 might be one of those cosmic trailblazers, its ultraviolet light helping to lift the veil on the universe's dark ages. Peering at GNZ11 is like holding up a mirror to our own origins. The elements it forged, carbon, oxygen, iron, would later recycle into generations of stars, planets, and eventually us. Its discovery pushes the boundaries of our telescopes and theories alike, forcing us to rethink how quickly the universe woke up from its silent beginnings. Every photon we capture from it is a message in a bottle, sent across 13.4 billion years, a reminder that the cosmos has always been more daring, more dynamic than we ever imagined. Those breathtaking spiral arms winding through galaxies like cosmic pinwheels, they're not what they seem. What looks like a permanent structure is actually an illusion, a stellar traffic jam frozen in time. Spiral arms are density waves, ripples of compressed gas and stars that move through galaxies like sound waves through air. Here's the twist: the stars themselves aren't fixed in those graceful curves. Instead, they drift in and out of the arms like cars merging through a slow-moving highway bottleneck. Picture a stretch of busy freeway where construction narrows lanes. Cars bunch up as they approach the bottleneck, moving slower and tighter together. But once they pass through, they speed up and spread out again. The congestion isn't made of the same cars, it's a pattern moving through the traffic. Spiral arms work the same way. As stars orbit a galaxy's center, they enter a density wave where gravitational forces pack them closer together. This compression triggers star formation, lighting up the wave with young, bright stars, the reason spiral arms appear so vivid. But the stars don't stay put. Over millions of years, they exit the wave, leaving behind the very gas clouds that'll birth the next generation of stars to keep the illusion alive. This explains why spiral arms don't wind up like over-twisted rubber bands. Without density waves, a galaxy's rotation would curl its arms tighter and tighter until they dissolved into chaos. Instead, the wave maintains the pattern, a self-renewing stellar conveyor belt. The Milky Way's own arms rotate at a different speed than its stars, while our Sun takes about 225 million years to orbit the galactic center. It's crossed spiral arms multiple times in Earth's history. Each passage may have bathed our solar system in denser interstellar material, potentially triggering comet showers or even influencing our planet's climate. The next time you see a galaxy's spiral, remember, you're witnessing a grand cosmic magic trick. The arms are fleeting gatherings of stars, a momentary sparkle in an endless dance, proof that even the most majestic structures in the universe are fluid, ever-changing, and far more dynamic than they appear. Not all galaxies whirl with the grace of spirals. Some loom like silent titans, glowing with the steady burn of ancient stars. Elliptical galaxies are the universe's retirees, their smooth, football-shaped profiles a stark contrast to the vibrant arms of their spiral cousins. Where spirals buzz with the blue light of young stars and swirling gas, ellipticals radiate a golden hue, their stars packed so tightly they form a dense, featureless glow. These galaxies aren't just different in appearance, they're cosmic relics, telling the story of violent pasts and quiet futures. The secret to their formation lies in chaos. While spiral galaxies like the Milky Way grow gradually, ellipticals are born from catastrophic collisions. Picture two spirals, each with billions of stars, slamming together in a gravitational embrace so fierce it scrambles their delicate structures. The collision doesn't just mix their stars, it disrupts the delicate balance of gas and dust needed to form new stars. Like throwing a wrench into a well-oiled machine, the merger triggers massive shockwaves that heat the gas, rendering it too turbulent to collapse into stellar nurseries. Over time, the once spiraling disks settle into a smooth, rounded shape, their remaining stars orbiting in random directions like a swarm of disoriented bees. What's left is a galaxy frozen in time. Without fresh gas to fuel star birth, elliptical galaxies become museums of aging stars. Their populations skew old and red, with few of the massive, short-lived blue stars that light up spirals. The brightest examples, called giant ellipticals, can dominate the centers of galaxy clusters, weighing in at over 100 trillion times the mass of our Sun. Their sheer size hints at a voracious past. Many likely grew by cannibalizing smaller galaxies, absorbing their stars without reigniting star formation. Yet even in their quietude, ellipticals hold surprises. Some harbor supermassive black holes more active than our Milky Ways, their last vestiges of violence flickering in X-rays as they slowly consume leftover gas. Others, known as rejuvenated ellipticals, show faint signs of recent star birth, suggesting they stole a snack of gas from a passing neighbor, but these are exceptions. For the most part, ellipticals are the cosmic equivalent of a grandparent's living room, warm, steady, and filled with the glow of a long life well lived. So the next time you see an elliptical galaxy in a telescope image, remember, its serene appearance belies a dramatic youth. It's a reminder that even in the universe, some things settle into quiet majesty after a lifetime of turbulence. Some galaxies don't just form stars, they explode with them. Imagine a cosmic fireworks show where instead of sparks, you get supernovas, and instead of minutes, the spectacle lasts millions of years. This is the reality of starburst galaxies like the Cigar Galaxy, where star birth isn't a gentle process but a full-blown eruption. Right now, in this jagged-edged galaxy 20 million light-years away, stars are igniting at a rate 10 times faster than in our Milky Way. If our galaxy were a quiet countryside, starburst galaxies would be downtown during rush hour, chaotic, crowded, and blazing with energy. What sets off these celestial fireworks? One word: pressure. Galactic collisions are the most common trigger. When two galaxies graze or merge, their gas clouds slam together like storm fronts, compressing until they reach a breaking point. Picture squeezing a balloon until it pops, except here, the pop is a chain reaction of stars bursting to life, but collisions aren't the only spark. Sometimes the death of one star lights the fuse for thousands more. In the Cigar Galaxy, supernovas explode so frequently, about once every 20 years, that their shockwaves act like cosmic bellows, heating and churning the surrounding gas. This creates a feedback loop. Each explosion triggers more star birth, whose most massive stars then explode in turn, keeping the cycle raging. The result is a galaxy on overdrive. Starburst regions glow intensely in infrared light, hidden behind thick curtains of dust stirred up by the chaos. The youngest stars here are often born in hyper-dense clusters, packed so tightly they'd make our night sky look like a spotlight compared to their stadium floodlights. And the sheer energy output is staggering enough to launch galactic winds, rivers of superheated gas streaming outward at millions of miles per hour. These winds can carve bubbles in the interstellar medium or even blow gas clean out of the galaxy, starving it of future star-forming material. Yet for all their violence, starbursts are fleeting. They burn bright but fast, exhausting their gas reserves in just tens of millions of years, a blink in cosmic time. What's left behind? A galaxy littered with the remnants of its explosive youth, supernova remnants, neutron stars, and eventually a quieter population of aging stars. The cigar galaxy's current frenzy won't last forever, but while it does, it's a dazzling reminder of how dynamic and how destructively creative the universe can be. Hidden in the depths of space, there are galaxies so faint you could stare right through them without noticing ghosts woven into the fabric of the cosmos. Meet ultra-diffuse galaxies like Dragonfly 44, a cosmic paradox as wide as the Milky Way but with only 1% of its stars. If our galaxy were a bustling metropolis, Dragonfly 44 would be a sprawling, empty warehouse, same square footage, just hauntingly vacant. These celestial phantoms defy everything we thought we knew about how galaxies form, and their existence has astronomers scratching their heads. How does something so large end up with so little? One clue lies in their dark matter. When astronomers first studied Dragonfly 44 rotation, they expected sluggish movement from its sparse stars. Instead, they found stars whipping around at speeds that should fling them into the void, unless, of course, an invisible halo of dark matter was anchoring them in place. Turns out Dragonfly 44 is 99% dark matter, a shadowy skeleton holding together a wispy veil of stars. It's like discovering a balloon that looks empty but weighs as much as a freight train. But why aren't these galaxies packed with stars like their brighter cousins? One theory points to a tragic cosmic miscarriage. Billions of years ago, ultra-diffuse galaxies might have been born with just as much gas as normal galaxies, but something robbed them of their future. Intense radiation from nearby quasars or supernovas could have scorched away their star-forming fuel early on, leaving them stranded as cosmic stillbirths. Others might have been victims of their environment, drifting through galaxy clusters where intergalactic winds stripped their gas away like sandblasting a mural down to bare brick. Yet some ultra-diffuse galaxies, like those in the isolated Coma cluster, flaunt another bizarre trait: they're inexplicably ancient. Their stars are nearly as old as the universe itself, suggesting they formed all at once in a frenzied burst, then stopped. No second acts, no new generations, just frozen in time like celestial museums. This has led to a radical idea. What if these galaxies aren't failed versions of normal ones, but relics of an entirely different galactic evolution path? A path where dark matter clumped differently in the early universe, creating vast star-poor realms that somehow survived to the present day. The mystery deepens when you realize we're likely only seeing the tip of the iceberg. Current telescopes can only spot ultra-diffuse galaxies that happen to be close enough or backlit by even more distant objects. There could be legions of them lurking undetected in the darkness, rewriting the story of galactic diversity. Every new discovery peels back another layer, revealing a universe far stranger and more varied than we ever imagined. Galaxies breathe, not in the way we do, but through colossal gusts of superheated gas that rush outward at millions of miles per hour. These aren't gentle breezes, they're hurricane-force tempests known as galactic winds, capable of reshaping entire galaxies. Picture a wildfire sweeping through a forest, clearing old growth to make way for new life, except here, the flames are powered by exploding stars and ravenous black holes, and the forest is a galaxy's worth of star-forming fuel. When a massive star dies in a supernova, it doesn't go quietly. The explosion hurls material outward with enough force to push surrounding gas out of the galaxy entirely. Multiply this by thousands of supernova in a starburst galaxy, and you've got a feedback loop of chaos. Gas gets heated, pressurized, and ejected like confetti in a wind tunnel, stripping the galaxy of the raw materials needed to make new stars. It's a self-regulating system. Too much star birth leads to too many explosions, which then shuts down star birth altogether. But supernova aren't the only architects of these winds. Supermassive black holes at galactic centers contribute their own fury. When these monsters feed, they don't just swallow matter quietly. They belch out jets of energy so intense they can blow gas across thousands of light years. Active galactic nuclei, or AN, create winds so powerful they carve cavities in intergalactic space, redistributing heavier elements like oxygen, carbon, and iron far beyond their home galaxies. These metals, forged in the hearts of stars and scattered by the winds, become the building blocks for future generations of stars and planets. The impact is staggering. In galaxy clusters like the Perseus cluster, astronomers have detected vast bubbles of gas, each spanning hundreds of thousands of light years, inflated by winds from the central galaxy's black hole. These bubbles act like cosmic pressure valves, preventing gas from cooling and collapsing into new stars too quickly. Without them, galaxies in dense clusters would burn through their fuel in a frenzy, leaving behind barren husks. Yet for all their destructive power, galactic winds are also creators. By seeding intergalactic space with metals, they enrich the cosmic web, ensuring that future galaxies and the life within them have the chemical diversity needed to thrive. Our own solar system might owe its existence to metals scattered by winds from long-dead stars in ancient galaxies. So while these winds may end one chapter of a galaxy's story, they're always writing the beginning of another. We think of galaxies as lonely islands in the void, but the truth is they clump together like families at a reunion. Our Milky Way belongs to one of these cosmic clans, the Local Group, a modest gathering of around 80 galaxies spanning 10 million light-years. And while that sounds vast in galactic terms, it's practically next-door neighbors. The real heavyweights here are Andromeda, our own Milky Way, and the elegant Triangulum Galaxy, three spirals locked in a slow gravitational dance that's been playing out for billions of years. Let's start with Andromeda, the big sister of our neighborhood, 2.5 million light-years away. It's the most distant object you can see with the naked eye on a clear night, appearing as a faint smudge of light. But don't let its gentle glow fool you. Andromeda is a titan, twice the size of the Milky Way, with 1 trillion stars swirling in its disk. Recent studies reveal it's had a violent past, devouring multiple smaller galaxies over its lifetime, their remnants strewn across its halo like cosmic crumbs. Then there's Triangulum, the understated middle child. Smaller and fainter than its siblings, this spiral galaxy is still nothing to scoff at. It boasts a dazzling star-forming region called NGC 604, one of the brightest stellar nurseries in the Local Group. What makes Triangulum fascinating is its delicate structure. Unlike Andromeda and the Milky Way, it hasn't been heavily disrupted by mergers, making it a pristine example of an undisturbed spiral galaxy. But the real drama lies in the dozens of dwarf galaxies orbiting these giants, the cosmic equivalent of kids clinging to their parents' legs. The Milky Way alone hosts at least 60 known dwarf galaxies, like the Large and Small Magellanic Clouds, visible from Earth's southern hemisphere. These galactic minnows aren't just decorative, they're vital to understanding galaxy evolution. Many are being slowly torn apart by tidal forces, their stars smeared into long streams that wrap around the Milky Way like celestial ribbons. Gravity is the invisible choreographer of this dance. The entire Local Group is bound together in a delicate balance, with Andromeda and the Milky Way gradually pulling closer while smaller galaxies orbit like moths around a flame. Computer simulations suggest that in the distant future, the local group will collapse entirely, merging into a single supergalaxy, a fate already playing out in other clusters across the universe. For now, though, we're part of a living celestial ecosystem where galaxies tug and twist each other in a slow-motion ballet. Every star in the night sky, every wisp of the Milky Way, is part of this grand, interconnected story, one where even the tiniest dwarf galaxy has a role to play. Every atom in your body was forged in the heart of a star, a fact so profound it borders on poetry. This is the universe's ultimate recycling program, where stars act as cosmic alchemists, transforming simple elements into the building blocks of everything from planets to people. It starts with the Big Bang, which left the early universe with little more than hydrogen, helium, and trace amounts of lithium. But today, we're surrounded by carbon, oxygen, iron, and gold. The difference: billions of years of stellar furnaces and cataclysmic explosions. Take our Sun, for example. Right now, deep in its core, hydrogen nuclei are crammed together under unimaginable pressure, fusing into helium and releasing energy. But this is just the first step. Larger stars, those with 8 times the mass of our Sun or more, become celestial pressure cookers. As they age, their cores grow hotter and denser, allowing them to fuse helium into carbon, carbon into oxygen, and so on, climbing the periodic table like a ladder until they reach iron. This process, called nucleosynthesis, is how the universe creates the elements that make up everything from the screen you're reading this on to the calcium in your bones. But here's the catch: stars can't fuse elements heavier than iron without losing energy. That's where supernova come in. When a massive star exhausts its fuel, its core collapses in less than a second, rebounding in an explosion so powerful it briefly outshines an entire galaxy. The shockwaves from this detonation are like a cosmic blender, churning the star's outer layers and bombarding nuclei with neutrons to create gold, platinum, uranium, elements so heavy only a supernova's fury can forge them. Then, in a final act of generosity, the explosion hurls these newly minted elements into space at nearly 1/10 the speed of light. These stellar ashes don't just vanish. They mingle with interstellar gas, enriching future generations of stars and planets. The Orion Nebula, for instance, glows with the light of young stars born from gas laced with elements from long-dead ancestors. Our own solar system is a testament to this cycle: the iron in Earth's core, the silicon in its rocks, and the oxygen you're breathing right now were all forged in stars that died before the Sun was born. Even the gold in your jewelry owes its existence to colliding neutron stars, events so rare and violent they're thought to be the universe's primary source of heavy elements. This recycling isn't just a historical footnote, it's ongoing. Right now, stars across the Milky Way are fusing elements that will one day be part of new worlds. Supernova continue to seed nearby nebulae with fresh material, and galactic winds carry these enriched gases across vast distances. The universe isn't just expanding, it's evolving, growing more chemically complex with each stellar generation. So the next time you look up at the night sky, remember, you're not just seeing points of light. You're witnessing a chain of cosmic inheritance stretching back to the very first stars, a story written in stardust and supernova, with every atom in your body as its latest chapter. In the early 20th century, Edwin Hubble peered through the world's most powerful telescope and saw something astonishing: galaxies weren't just random smudges of light. They had patterns, structures, a hidden order waiting to be deciphered. His solution, the Hubble sequence, a cosmic filing system that sorted galaxies into neat categories like a librarian organizing books by genre. At its core, the system splits galaxies into 3 broad families: spirals with their elegant windmill arms, ellipticals, the smooth, featureless giants, and irregulars, the misfits that refuse to fit in. It was a simple framework, but one that revolutionized our understanding of the universe's architecture. Spiral galaxies like our Milky Way became the darlings of the sequence. Hubble noticed they came in two flavors: those with a bright central bar, imagine a starry T-bone steak, and those without. His classification even accounted for how tightly their arms were wound, from A, loose, open spirals, to D, tightly coiled. But here's what he couldn't have known then: those arms aren't static. They're dynamic waves, as we've seen, with stars drifting in and out like commuters passing through a train station. Ellipticals, on the other hand, were labeled from E0 to E7 based on how stretched they appeared, from perfect spheres to flattened footballs. Hubble initially thought this sequence represented an evolution, that galaxies might start as spirals and slowly deflate into ellipticals over time. We now know it's not that simple. Ellipticals often form through violent mergers, their stars scrambled into new orbits, while spirals thrive in quieter cosmic neighborhoods. The sequence wasn't a timeline, it was a snapshot of galactic diversity. Then there were the irregulars, the cosmic rebels. Hubble originally treated them as outliers, but modern telescopes have revealed they're anything but rare. Dwarf irregulars, for instance, are among the most common galaxies in the universe. Their chaotic shapes a testament to turbulent histories, some ripped apart by tidal forces, others stunted by stolen gas. Even the Large Magellanic Cloud, our Milky Way's largest satellite, was once considered irregular until we spotted a faint, hidden bar lurking in its heart. The Hubble sequence was just the beginning. Today, we've discovered galaxies that defy his categories entirely. Ring galaxies like Hoag's object, a perfect circle of stars with a gaping hole in the middle. Ultra-diffuse galaxies so ghostly they're barely visible. And even jellyfish galaxies trailing tentacles of stars, stripped bare by the brutal winds of galaxy clusters. Hubble's framework wasn't wrong, it was incomplete, a first draft in a story that keeps growing richer. What makes the sequence endure isn't its rigidity, but its flexibility. Astronomers still use it as a shorthand, a way to start conversations about galactic anatomy. But now we understand that galaxies, like living things, resist simple labels. They're shaped by collisions, star births, black holes, and dark matter forces that sculpt them into forms Hubble could never have imagined. His sequence wasn't the final word on galaxies. It was the key that unlocked our curiosity, inviting us to look deeper and ask, what else is out there? Somewhere in the darkness beyond our galactic neighborhood, an invisible hand is tugging us toward the unknown. The Milky Way, along with thousands of nearby galaxies, is racing through space at over 1 million miles per hour. Not just from the expansion of the universe, but toward something colossal lurking behind the curtain of stars. Astronomers call this phenomenon the Great Attractor, a gravitational mystery so powerful it bends the paths of entire galaxies like rivers flowing toward a hidden sea. The strangest part, we can't even see it. The Great Attractor lies in the direction of the constellation Centaurus, but our view is blocked by the Milky Way's own dusty bulge, a cosmic case of standing too close to the painting to see the whole mural. What we do know comes from measuring the motion of galaxies. Just as leaves caught in a current reveal the flow of a river, galaxies drifting toward this unseen force betray its presence. Based on their trajectories, whatever's pulling us must have the mass of tens of thousands of Milky Ways concentrated in a region of space roughly 300 million light-years across. So what could it be? The leading theory points to the Norma cluster, a dense gathering of galaxies nicknamed the core of the Great Attractor. But here's the catch: even that massive cluster doesn't account for all the gravitational pull we're feeling. Some hidden structure, perhaps a web of dark matter or a supercluster we've yet to map fully, must be amplifying its grip. Recent studies suggest an even grander culprit: the Shapley supercluster, the most massive concentration of galaxies in our local universe, lying 650 million light-years away. Like a mountain hidden by fog, its gravity might be reaching across cosmic distances, pulling us and the Great Attractor itself toward it in a chain reaction of celestial motion. This revelation upends an old assumption that on large scales, the universe's expansion should smooth out all motion. Instead, we're finding that space is lumpy, with titanic structures wielding gravitational influence far beyond their visible edges. The Great Attractor isn't just pulling us, it's part of a vast cosmic tug-of-war where superclusters compete for dominance like continental plates shifting in slow motion. What does this mean for our galaxy's future? In the short term, cosmically speaking, very little. The forces at play unfold over hundreds of millions of years. But in the grand scheme, it's a humbling reminder that even our mighty Milky Way is adrift in currents larger than we can fully comprehend, drawn toward a destination we've only begun to glimpse. The Great Attractor isn't just a scientific puzzle, it's a compass pointing to the next chapter in our universe's untold story. Scattered like celestial time capsules around galaxies like our own, globular clusters might look like simple balls of stars, but they're actually among the oldest relics in the universe. These dense spherical swarms, each packing hundreds of thousands of stars into a space just a few dozen light-years across, are galactic fossils preserving snapshots of the universe's childhood. While the Milky Way itself has evolved over billions of years, spiraling, merging, and birthing new stars, globular clusters have remained eerily unchanged, their stars frozen in time like insects trapped in amber. What makes these clusters so special? Their stars are cosmic senior citizens, formed when the universe was a fraction of its current age. While typical stars in our galaxy's disk might be a few billion years old, globular cluster stars often clock in at 12 to 13 billion years, older than the Milky Way itself. They're made almost entirely of hydrogen and helium, the pristine ingredients of the early cosmos, with barely a trace of heavier elements. This purity makes them living laboratories for studying the first generations of stars before supernova had peppered the universe with metals. But here's where it gets fascinating. Globular clusters aren't just old, they're witnesses to galactic violence. Many of them orbit in the Milky Way's halo, tracing paths that suggest they weren't born here but were kidnapped during ancient collisions. Take Omega Centauri, the brightest globular cluster visible from Earth. Its stars vary wildly in age and composition, hinting it might be the stripped-down core of a dwarf galaxy devoured by the Milky Way long ago. Other clusters, like M54, are now known to belong to the Sagittarius dwarf galaxy, currently being torn apart by our galaxy's gravity. These clusters are like celestial breadcrumbs, marking the trails of galactic cannibalism across cosmic time. Their survival is a mystery in itself, packed so tightly that stars occasionally collide. Globular clusters should have dissolved over eons, yet here they are. The secret might lie in their extreme density, which creates a gravitational safety net. Over time, lighter stars get flung outward while heavier ones sink to the core, a process called dynamical friction that somehow stabilizes the cluster against disintegration. Some even harbor rogue black holes at their hearts, whose gravity might act like anchors, keeping the stellar swarm intact. By studying these ancient clusters, astronomers have uncovered unexpected twists in galactic history. Some contain multiple generations of stars, suggesting they somehow held onto enough gas to form new stars long after their birth. Others, like those orbiting the Andromeda galaxy, are far younger than expected, challenging assumptions about when and how galaxies assemble their entourages. Each cluster is a piece of a puzzle, helping us reconstruct the chaotic early years of galaxy formation, one fossilized star at a time. So next time you spot a globular cluster through a telescope, remember, you're not just seeing a pretty ball of light. You're glimpsing a relic from a time when the universe was in its infancy, a silent survivor of the cosmic storms that shaped everything we know. Magnetic fields are the silent architects of galaxies, invisible threads weaving through the cosmos with a subtle but undeniable influence. While gravity and dark matter dominate discussions of galactic structure, these fields, stretching tens of thousands of light years across spiral arms, play a surprisingly hands-on role in how galaxies evolve. Picture a galaxy's magnetic field like an enormous, delicate spiderweb, its strands tracing the contours of spiral arms and guiding the flow of gas with ghostly precision. Take star formation, for example. Gas clouds collapsing into new stars don't just battle gravity, they wrestle with magnetism too. As a cloud condenses, magnetic fields resist the crush, creating a cosmic tug-of-war. For stars to ignite, gas must shed its magnetic shackles, either by slipping particles through the field lines like beads on a string, or through a process called magnetic reconnection, where fields snap and rearrange like overstretched rubber bands. This explains why star-forming regions often coincide with tangled magnetic knots. The fields are literally being pushed to their limits, but magnetism's reach goes further. Spiral arms, those grand cosmic pinwheels, owe part of their crisp definition to magnetic fields. Observations from radio telescopes reveal that fields align parallel to these arms, acting like cosmic guardrails that channel gas flows and stabilize the structure. Without this invisible scaffolding, spiral arms might dissolve into chaos far faster than density waves alone could sustain. The Milky Way's own magnetic field, measured through the polarization of starlight, shows a striking alignment with its spiral pattern. No coincidence, but a clue to how galaxies maintain their iconic shapes over billions of years. Even the fate of entire galaxies can hinge on these fields. When galaxies collide, their magnetic fields don't just passively follow, they amplify. Turbulence from the merger stretches and twists field lines, creating a feedback loop that accelerates particles to near-light speeds. The result, galactic-scale particle accelerators that glow in radio waves, painting vivid portraits of magnetic mayhem. The antennae galaxies, a famous merging pair, showcase this beautifully, their entangled magnetic fields sparking bursts of star formation while funneling gas into colossal shock fronts. What's truly humbling is how recently we've begun to unravel this magnetic tapestry. For decades, galaxy models treated magnetism as an afterthought, too faint, too diffuse to matter. But new instruments like the Square Kilometre Array and the Atacama Large Millimeter Array are revealing fields far stronger and more organized than predicted, threading through even the emptiest galactic voids. They're not just bystanders, they're active players in the cosmic drama, shaping galaxies from the inside out. So the next time you gaze at a spiral galaxy's graceful arms, remember, there's an invisible force at work, one that guides, resists, and ultimately helps sculpt the universe's most breathtaking structures. Magnetic fields may be silent, but their impact echoes across the cosmos. If galaxies are cities of stars, then galaxy clusters are the sprawling megacities of the cosmos, vast metropolises where thousands of galaxies huddle together, bound by gravity in a dance that reshapes them all. Take the Virgo cluster, the nearest major gathering of galaxies to our Milky Way. Within its 10 million light-year span, over 2,000 galaxies jostle for space, their combined mass so immense it bends the fabric of spacetime itself. And yet, the galaxies aren't even the most dramatic feature here. Between them, a searing hot plasma called the intracluster medium roils at temperatures of up to 100 million degrees, so energetic it glows not in visible light but in X-rays. This intergalactic inferno is no accident. Over billions of years, galaxies orbiting the cluster's core have shed gas through collisions, supernova winds, and the relentless pull of gravity. The result, a diffuse ocean of supercharged particles, laced with heavy elements forged in stellar furnaces, essentially, the recycled remains of countless dead stars. The Chandra X-ray Observatory has captured this medium in stunning detail, revealing intricate structures like shock waves and cavities carved by jets from supermassive black holes. It's a cosmic recycling plant on the grandest scale, where gas stripped from galaxies eventually cools and falls back inward, fueling new generations of stars. But the real spectacle is how the intracluster medium shapes the galaxies themselves. Spirals entering the cluster's dense core face a brutal gauntlet known as ram pressure stripping. Imagine holding a balloon out of a car window. The rushing wind peels away the outer layers. In the Virgo cluster, the intracluster medium acts like that wind, ripping gas from galaxies as they plunge through it. The iconic jellyfish galaxy JO206 is a prime example, trailing tendrils of star-forming gas like cosmic tentacles as it battles the cluster's tides. Over time, this process can transform gas-rich spirals into gas-poor ellipticals, explaining why cluster cores are dominated by these smooth, aging giants. The Coma cluster, another cosmic colossus 6 times farther away, takes this drama to extremes. Home to over 10,000 galaxies, it's a hive of activity where gravitational interactions fling galaxies into chaotic orbits. X-ray images show the intracluster medium here isn't uniform. It's streaked with filaments and bubbles, evidence of past mergers and black hole outbursts. One of its most famous residents, the galaxy NGC 4921, spins in eerie slow motion, its star formation nearly quenched by the cluster's relentless environment. What's fascinating is how these clusters evolve. Simulations suggest they grow like avalanches, smaller groups of galaxies merging hierarchically over time. The intracluster medium bears scars of this history. The Perseus cluster, for instance, hosts sound waves, yes, actual sound waves in space propagating through its gas, likely triggered by ancient collisions. These waves transport energy, helping regulate the cluster's temperature and preventing runaway cooling that could otherwise flood the core with new stars. Galaxy clusters are more than just cosmic curiosities, they're time capsules. By studying their X-ray halos, astronomers can trace the flow of cosmic ingredients, weigh entire clusters revealing their hidden dark matter, and even test Einstein's relativity on scales he never imagined. They remind us that galaxies don't exist in isolation, but are part of a grand, interconnected web, one where even the emptiest spaces between them hum with invisible energy, shaping the destiny of everything they touch. Some galaxy clusters hide a cosmic secret. They weren't always the quiet, red-dominated neighborhoods they appear to be today. Back in the 1970s, astronomers Beverly Oemler and William Butcher made a startling discovery. When they peered at distant clusters, those so far away we see them as they looked billions of years ago, they found something unexpected, a surprising abundance of blue galaxies blazing with young stars. Fast forward to the present, and those same clusters are dominated by red, aging galaxies. This shift, now called the Butcher-Oemler effect, is one of the clearest signs that galaxy clusters aren't static. They're dynamic ecosystems evolving dramatically over cosmic time. So what flips a galaxy from blue to red? The answer lies in the brutal environment of a cluster. Imagine moving from a quiet countryside to the heart of a bustling metropolis. The rules change entirely. In the early universe, galaxies entering clusters were gas-rich, their spiral arms teeming with star-forming clouds. But as they fell into the cluster's gravitational grip, they faced a galactic version of culture shock. First came ram pressure, stripping, the same violent process we see today in clusters like Virgo, where the intracluster medium acts like a cosmic sandblaster, tearing away a galaxy's gas reserves. No gas means no new stars, leaving only the older, redder stars to fade slowly. Then there's harassment. In dense clusters, galaxies don't just drift peacefully, they zoom past each other at thousands of miles per second, their gravity tugging and distorting one another in fast, disruptive encounters. These flybys can destabilize a galaxy's delicate structure, either triggering bursts of star formation that exhaust its remaining fuel or scattering its gas so thoroughly it can't collapse into new stars. Over time, repeated encounters transform vibrant spirals into featureless ellipticals, their star-forming fires snuffed out. But here's the twist: not all galaxies succumb equally. The Butcher-Ohmler effect shows that the fraction of blue galaxies peaks at around halfway through the universe's current age, a sweet spot where clusters were assembling rapidly, pulling in fresh spirals faster than they could be quenched. Today, that influx has slowed, and the few remaining blue galaxies are often newcomers, still holding onto their gas as they plunge into the cluster's outskirts. This cosmic metamorphosis isn't just about destruction, it's about transformation. The same processes that strip galaxies of their star-forming fuel also enrich the intracluster medium with heavy elements, seeding future generations of stars and planets. The Butcher-Ohmler effect is like finding fossilized footprints in the sand, a trail of evidence showing how galaxies, like living things, adapt or perish in the face of their environment. And it's a stark reminder that even the grandest structures in the universe are works in progress, forever shaped by the invisible hand of time. The universe has a math problem, one that's been puzzling astronomers for decades. According to our best simulations of dark matter, giant galaxies like the Milky Way should be surrounded by thousands of tiny satellite galaxies, each held in orbit by its own halo of invisible mass. But when astronomers actually count them, the numbers don't add up. We've found barely a few dozen, leaving a glaring gap between prediction and reality. This cosmic conundrum is known as the missing satellite problem, and solving it could force us to rethink everything we know about dark matter, or even uncover entirely new physics. To understand why this matters, picture dark matter as the scaffolding of the universe. After the Big Bang, it clumped together first, creating gravitational wells that ordinary matter, gas, dust, and eventually stars flowed into. Supercomputer simulations like the famous Millennium Run show this process in action, tracing how dark matter halos of all sizes should have seeded galaxies big and small. The math suggests our Milky Way alone should host thousands of dwarf galaxies, each tethered to its own dark matter pocket. Yet in reality, we've catalogued fewer than 60. Where are the rest? One possibility is that we're just not seeing them. Many predicted dwarfs could be so faint, so star-poor, they're effectively invisible to current telescopes. Recent discoveries back this up. Ultra-faint dwarfs like Segway 1, with a few hundred stars spread over a volume hundreds of light-years wide, were only detected in the past decade thanks to painstaking surveys. Others might be lurking behind the Milky Way's dusty disk, hidden from view like fireflies behind a curtain. The Dark Energy Survey and upcoming projects like the Vera Rubin Observatory are hunting these ghosts, peeling back the cosmic veil one pixel at a time. But there's a catch. Even as we find more dwarfs, their properties don't quite match predictions. Simulations suggest dark matter halos should be dense at the center, yet many observed dwarfs seem oddly puffy, with stars scattered more diffusely than expected. This has led to radical ideas. Maybe dark matter isn't as cold as we thought. The standard model assumes dark matter particles move sluggishly, but if they're warmer and faster, they'd form fewer, looser clumps, potentially explaining the satellite shortage. Others propose dark matter interacts with itself or with regular matter in ways we haven't accounted for, subtly altering how galaxies form. Then there's the nuclear option. What if dark matter doesn't exist at all? A handful of scientists argue for modified Newtonian dynamics, or MUND, a theory that tweaks gravity itself to explain galactic rotations without invoking invisible mass. But MUND struggles to replicate the large-scale structure of the universe, leaving most astronomers convinced dark matter is real or just stranger than we imagined. The missing satellites aren't just a counting exercise, they're a stress test for our entire understanding of cosmic evolution. Every faint dwarf we discover, every mismatch between theory and observation, is a clue, a whisper from the universe urging us to look deeper. Whether the answer lies in better telescopes, new physics, or something entirely unexpected, one thing's certain: the cosmos still holds cards it hasn't shown us yet. In the darkest corners of the early universe, cosmic monsters were throwing tantrums of unimaginable fury, and we can still see their tantrums from billions of light years away. These are quasars, the brightest objects in existence, capable of outshining entire galaxies with the glare of 1,000 suns. But what makes them truly fascinating isn't just their brilliance, it's what they reveal about the chaotic adolescence of galaxies. Every quasar is powered by a supermassive black hole in its rebellious phase, gorging on gas so violently that the infalling material heats up to millions of degrees, creating a blazing disk of light visible across the cosmos. Think of a quasar as a black hole's growth spurt. In the early universe, when galaxies were young and gas was plentiful, supermassive black holes at their centers feasted unchecked. As matter spiraled inward at nearly light speed, friction turned the black hole's dining room into an incandescent furnace, converting gravity directly into radiation. The energy released wasn't just light, it was a firestorm of X-rays and radio waves, so intense it could sterilize entire regions of space, shutting down star formation in its host galaxy. Yet paradoxically, these same outbursts might have also triggered star birth farther out, their shockwaves compressing gas clouds into stellar nurseries on the galactic fringe. What makes quasars cosmic gold mines is how they illuminate the distant past. Because light takes time to travel, gazing at a quasar is like opening a window to the universe's toddler years. The most distant known quasar, J1342+0928, shines from a time when the universe was barely 700 million years old, yet its black hole already weighed in at 800 million solar masses. That shouldn't be possible under traditional growth models, forcing astronomers to rethink how black holes could bulk up so quickly. Some suspect direct collapse, gas clouds so dense they skip the star stage entirely, imploding straight into black hole seeds, while others theorize early black holes merged at breakneck speeds, snowballing into giants in cosmic blink. Quasars also act as backlights, casting shadows that reveal the universe's chemical evolution. Their light passes through clouds of intergalactic gas, imprinting absorption lines that show how heavy elements gradually enrich the cosmos. Without quasars, we might never have realized that the universe was fully ionized, its hydrogen fog burned away by the time it reached 1 billion years old. Even their decline tells a story. As the universe aged and galaxies settled down, quasars became rarer, not because black holes disappeared, but because they ran out of messy meals. Today's supermassive black holes, like our Milky Way Sagittarius A, are mostly quiet, their quasar days long over. So when astronomers spot a quasar flickering in the depths of space, they're seeing more than a cosmic beacon. They're witnessing a galaxy's fiery growing pains, a black hole's brief but spectacular reign of terror, one that shaped everything from star formation to the distribution of galaxies we see today. These celestial lighthouses don't just show us where the early universe burned brightest, they illuminate how chaos sculpted order in the darkness. If you could zoom out far enough to see the universe on the grandest scale, you wouldn't see galaxies scattered randomly like sprinkles on a cupcake. Instead, you'd witness an intricate, luminous web, a vast cosmic tapestry where galaxies cling to glowing filaments like dewdrops on a spider's silk. This is the cosmic web, the universe's fundamental architecture, and it reveals a truth more astonishing than anyone imagined. Galaxies aren't isolated islands. They're beads strung along invisible threads of dark matter, woven together across billions of light years in a pattern so immense it defies human intuition. The cosmic web's blueprint was set in motion mere moments after the Big Bang. Microscopic quantum fluctuations, tiny ripples in the newborn universe, stretched to cosmic proportions as space expanded, creating regions where dark matter clumped ever so slightly denser. Over billions of years, gravity amplified these differences, pulling dark matter into sprawling filaments that intersect at dizzying hubs called nodes. Ordinary matter, the gas that would become stars and galaxies, simply followed the dark matter's lead, flowing along these hidden highways and pooling where filaments crossed. The result, a universe structured like a sponge, with galaxies nesting along filaments and congregating at nodes, while vast, empty voids stretch between them. Maps of the cosmic web, like the Sloan Digital Sky Survey, reveal its staggering complexity. One of the largest known structures, the Hercules Corona Borealis Great Wall, spans 10 billion light-years, a filament so colossal it challenges our understanding of cosmic limits. Zooming in closer, galaxy clusters like Laniakea, the supercluster containing our Milky Way, show how even these titanic structures are just knots in the web's grander weave. And here's the humbling part. What we see, the glittering galaxies, is less than 10% of the story. The real framework is the dark matter scaffolding, invisible yet dictating where galaxies can form, live, and collide. This structure isn't static, it's a dynamic, evolving network. Computer simulations like the Illustris TNG project show filaments acting as cosmic pipelines, funneling gas toward hungry galaxies and supermassive black holes. When two filaments intersect, the resulting shockwaves can trigger bursts of star formation, lighting up nodes with stellar fireworks. Meanwhile, the voids, the web's empty stretches, aren't truly empty. They're just underdeveloped, like rural towns bypassed by the interstate. Their sparse gas never got the gravitational nudge to collapse into galaxies, leaving them dark and quiet. The cosmic web does more than shape galaxies, it shapes our very understanding of the universe. By tracing its filaments, astronomers have weighed the cosmos, confirming the existence of dark matter and dark energy. Its structure is a fossil record, preserving the universe's initial conditions like tree rings chronicling millennia. And perhaps most poetically, it connects us. The Milky Way's local filament threads through Virgo and Laniakea, linking us to a neighborhood that stretches hundreds of millions of light-years, proof that even in the vastness of space, nothing is truly alone. When galaxies collide, they don't just destroy, they create. Amid the chaos of a celestial smash-up, something extraordinary can happen. New galaxies are born from the wreckage. These cosmic orphans, known as tidal dwarf galaxies, aren't forged from primordial gas like their ancestors. Instead, they're stitched together from the debris of galactic collisions. Streams of stars and gas torn loose by gravitational violence, then left to clump together in the void. Take the Tadpole Galaxy, a pinwheel-shaped spiral with a tail stretching 280,000 light-years behind it. That tail isn't just debris. It's a stellar nursery where at least 4 new tidal dwarfs are taking shape, each one a tiny island of order emerging from the chaos. What makes these galaxies special is how they defy expectations. Unlike traditional dwarfs, which form in the halos of dark matter, tidal dwarfs are almost pure baryonic matter, stars and gas ripped free from their parent galaxies. Without dark matter's gravitational anchor, they should be fragile, dissipating back into the void, yet somehow they endure. The secret lies in their birth. When two galaxies graze each other, their tidal forces, the same pull that creates ocean tides on Earth, stretch their gas and stars into long arcs. In these streams, pockets of gas collapse under their own gravity, igniting new stars whose radiation heats the surrounding material, creating pressure bubbles that help the structure hold its shape. Over millions of years, these knots grow dense enough to become self-contained galaxies, complete with their own star-forming regions and even orbiting satellite clusters. One of the most studied examples, NGC 5291, showcases this process in action. Nearly 360 million years ago, a high-speed collision ejected a ring of gas from this galaxy, a ring that later fragmented into a dozen tidal dwarfs. Observations from the Very Large Telescope revealed something astonishing. These dwarfs are rich in heavy elements like oxygen and neon, proving they formed from recycled material expelled by their parent's disk, not pristine intergalactic gas. That makes them cosmic upcyclers, turning the ashes of older stars into new stellar frontiers. But here's the twist: tidal dwarfs might be more than just curiosities. Some astronomers suspect they could solve a long-standing mystery: the abundance of isolated dwarf galaxies found floating in voids far from any major galaxy. Traditional models struggle to explain how these loners formed, but if they're the survivors of ancient collisions, their existence suddenly makes sense. The tadpole's tail, for instance, will eventually drift free of its parent, leaving its fledgling dwarfs to wander intergalactic space alone. Over billions of years they'll fade, their star formation sputtering out as gas reserves deplete, but their very presence rewrites the rules of galactic survival. What's truly humbling is realizing that these tiny galaxies are time capsules. The stars within them carry the chemical fingerprints of their violent birth, preserving a record of the collision that created them long after the parent galaxies have merged into anonymity. They're proof that destruction and creation are two sides of the same cosmic coin, and that even in the vastness of space, nothing truly goes to waste. Our sun isn't just floating aimlessly through space, it's on an epic, slow-motion joyride around the Milky Way, carrying Earth and the entire solar system along for the ride. Picture this: every 230 million years, our sun completes one full orbit around the galactic center, tracing a path so vast it makes the journey of planets around stars seem trivial. Since our solar system formed 4.5 billion years ago, we've made about 20 laps around the galaxy, which means, astronomically speaking, we're celebrating our 20th galactic birthday. But this isn't a simple, flat circle like a racetrack. The sun's path is more like a cosmic roller coaster, bobbing up and down through the Milky Way's disk as it travels. This vertical motion is one of the most fascinating yet overlooked parts of our galactic journey. As the sun orbits, it doesn't stay perfectly aligned with the galactic plane, that thin, pancake-like layer where most of the Milky Way's stars, gas and dust reside. Instead, it oscillates above and below the plane like a dolphin leaping through waves, completing a full up and down cycle roughly every 60 million years. Right now, we're actually above the plane by about 75 light-years, a stone's throw in galactic terms, and currently climbing higher before gravity will inevitably pull us back down. What causes this undulating motion? It's all about the Milky Way's gravitational tug-of-war. The galactic disk isn't uniform, it's littered with dense molecular clouds, spiral arms, and the invisible pull of dark matter. As the sun moves through these regions, their collective gravity nudges it slightly off course, creating this rhythmic rise and fall. Think of it like walking across a trampoline with weights scattered around. Your path would dip and rise depending on where you step. Here's where it gets even more intriguing. Some scientists speculate these oscillations could influence life on Earth. As the sun plunges through the denser parts of the galactic plane, our solar system encounters more interstellar dust, gas, and possibly even gravitational disturbances from nearby stars. Some theories suggest these passages might coincide with mass extinction events, as increased cosmic radiation or comet showers bombard our planet, the last time we crossed the plane. Roughly 3 million years ago, around the same time, the Earth's climate began shifting toward the ice ages. Coincidence? Maybe, but it's a tantalizing clue that our place in the galaxy might subtly shape life's trajectory in ways we're only beginning to understand. Meanwhile, our orbital speed is nothing to scoff at. We're hurtling around the galactic center at about 515,000 miles per hour. Yet because the Milky Way is so mind-bendingly large, this feels less like racing and more like being stuck in cosmic traffic. The Andromeda galaxy, by comparison, is zooming toward us at nearly 250,000 miles per hour, yet its collision with the Milky Way won't happen for 4 billion years. That's how much empty space dominates even a crowded galaxy. As we continue our leisurely spiral around the Milky Way, we're also subtly swayed by the galaxy's spiral arms. These density waves regions where stars and gas are temporarily packed tighter exert a gentle gravitational pull, potentially nudging the Sun's orbit over eons. Some models suggest our solar system may have migrated inward from a birth location farther out, meaning the Earth's galactic address wasn't always the same. It's a humbling thought. The ground beneath your feet, the air you breathe, even the sunlight warming your skin are all part of an ancient, slow-motion voyage through a galaxy we're only beginning to map in detail. So the next time you look up at the Milky Way's shimmering band across the night sky, remember, you're not just a spectator, you're a passenger on a galactic carousel, riding a path sculpted by gravity, time, and the invisible architecture of dark matter, a journey so grand it makes even the lifespan of civilizations seem like the blink of an eye. Think of the night sky as a puzzle with billions of pieces, and now imagine trying to sort them all by hand. That's essentially the challenge astronomers faced before projects like Galaxies came along. With telescopes capturing millions of galaxy images faster than experts could analyze them, scientists turned to an unexpected resource, the curiosity of everyday people. What started as a simple online experiment in 2007 became one of the most transformative citizen science projects in history, proving that the collective power of human intuition could uncover cosmic secrets even supercomputers might miss. At its core, Galaxy Zoo was elegantly straightforward. Volunteers, anyone with an internet connection and a love for space, were shown images of galaxies from surveys like the Sloan Digital Sky Survey and asked to classify their shapes, spiral, elliptical, or something more unusual. No PhD required, just a keen eye and a willingness to contribute. But what happened next stunned the scientific community. Within months, over 50,000 participants had classified millions of galaxies, a task that would have taken a single researcher decades. The data revealed patterns in galaxy evolution that textbooks had missed, like the surprising correlation between a galaxy's color and its shape. But the real magic lay in the outliers, the strange, inexplicable objects only human eyes could flag as special. Enter Hanny's voorwerp, Dutch for Hanny's object, a cosmic oddity so bizarre it might have languished in obscurity without a sharp-eyed teacher named Hanny van Arkel. While scanning through Galaxy Zoo images, she spotted a glowing green blob adjacent to a distant spiral galaxy. It wasn't a star, it wasn't a galaxy, and it certainly didn't match any known classification. Astronomers, intrigued by her find, trained telescopes on the voorwerp and uncovered something extraordinary. It was a cosmic ghost. The eerie glow came from gas ionized by a quasar's long dead beam, a flashlight shining from a black hole that had since gone dark, its light echo fossilized in interstellar space. This wasn't just a new object, it was a snapshot of a galaxy's violent past, a clue to how black holes flicker on and off over cosmic timescales. Galaxy Zoo's legacy goes far beyond one discovery. The project birthed an entire ecosystem of citizen science, from classifying Martian terrain to tracking solar storms. It revealed how human brains evolved to spot patterns in chaos, excel at recognizing anomalies algorithms might dismiss. Volunteers have identified galaxy collisions, rare red spirals, and even a new class of compact star-forming galaxies dubbed green peas. Some participants, like Hanny, became co-authors on peer-reviewed papers, blurring the line between amateur and professional in the best possible way. What's most inspiring is how these collaborations reshape who gets to participate in science. When a retired nurse in Wisconsin or a high school student in Mumbai can help uncover the universe's mysteries, it democratizes discovery itself. The next breakthrough might not come from a mountaintop observatory, but from someone scrolling during their coffee break, proof that the cosmos speaks a language anyone can learn if we're just willing to listen. For nearly 400,000 years after the Big Bang, the universe was a featureless fog, a silent, lightless expanse where hydrogen atoms floated undisturbed in the cosmic dark. Then something extraordinary happened. Between 500 million and 1 billion years after creation, the cosmos underwent a radical transformation known as the epoch of reionization, when the first galaxies and stars flickered to life and lit a fire that would change everything. Their fierce ultraviolet radiation blasted through the primordial hydrogen like a cosmic sunrise, tearing electrons from atoms and turning the universe's opaque haze into the transparent sea of ionized gas we know today. This wasn't a gentle process, it was a violent rebirth. Picture the early universe as a vast, shadowy forest with young galaxies like scattered campfires at first. But as more ignited, their combined UV light acted like a slow-moving wildfire, burning away the hydrogen fog in expanding bubbles of clarity. The key players here were massive, short-lived stars, dozens of times heavier than our Sun, burning so hot their ultraviolet rays could strip electrons from hydrogen atoms with ease. Quasars, those brilliant black hole beacons, likely helped too, their piercing beams drilling tunnels of ionized gas through the darkness. Over hundreds of millions of years, these bubbles merged until the entire cosmos was alight, ending the so-called cosmic dark ages and ushering in the transparent universe we see today. But how do we know this happened? The evidence comes from some of the most distant quasars ever observed. Their light, traveling for over 13 billion years, carries telltale absorption lines, dark gaps in their spectra where neutral hydrogen once soaked up specific wavelengths. The farther back we look, the more these forests of lines thicken, revealing patches of lingering fog. Then, abruptly around redshift 6, about 1 billion years after the Big Bang, the lines vanish. The fog has lifted. Here's the puzzle. Reionization shouldn't have been easy. Hydrogen atoms love to recombine, like magnets snapping back together. To keep the universe ionized, early galaxies needed to produce UV photons at a staggering rate, far more than today's galaxies do. This suggests the first stars weren't just different, they were extreme. Born from pure hydrogen and helium, lacking heavy elements to cool their gas clouds, they likely formed as giants hundreds of times the Sun's mass, living fast and dying in supernovas that seeded the cosmos with its first metals. Yet even now, mysteries remain. Did dwarf galaxies, far more numerous than giants, dominate reionization, or was it driven by rare, brilliant quasars? The answer may lie in the faintest galaxies, too dim for current telescopes, but waiting to be revealed by the James Webb Space Telescope's infrared eyes. What's certain is that this epoch wasn't just a transition, it was the moment the universe woke up, its atoms forever changed, its destiny set. The very fact that we can peer back to this era means the light of those first galaxies won, and their victory is why we're here to see it at all. Among the countless galaxies dotting the cosmos, a rare few wear their history like a cosmic fingerprint: ring galaxies, those perfect bullseyes that look more like celestial dartboards than islands of stars. Hoag's object, discovered in 1950 by astronomer Art Hoag, is the pin-up model for these peculiar structures, a brilliant yellow core floating serenely inside a near-perfect circle of young blue stars, separated by a dark, almost empty gap. At first glance, it seems impossible. How could nature sculpt something so geometrically precise? The answer lies in one of the universe's most violent acts, a head-on galactic collision that turns chaos into eerie symmetry. Picture two galaxies on a catastrophic blind date, their centers aimed directly at each other like cosmic crosshairs. When one plunges through the heart of another, what astronomers call a bullseye collision, the gravitational shockwaves ripple outward like stones dropped in a pond. The intruder's gravity disrupts the victim galaxy's disk, flinging stars and gas outward in an expanding ring while leaving the central bulge relatively untouched. But here's the twist: the intruder doesn't stick around. Simulations show it often sails straight through, escaping the scene like a galactic hit-and-run driver, leaving behind a shimmering ring as the only evidence of its passage. Over millions of years, the displaced material begins to clump under its own gravity. igniting new stars that trace the ghostly outline of that initial impact. Ring galaxies aren't just curiosities, they're celestial laboratories. The Cartwheel Galaxy, another famous example, showcases how these collisions trigger starbursts on an epic scale. Its outer ring, a riot of young blue stars and glowing pink hydrogen clouds, is essentially a galactic maternity ward where compressed gas from the collision erupts into newborn stars. Meanwhile, the gap between the core and the ring acts like a time capsule. The older, redder stars near the center tell us what the galaxy looked like before the crash, while the vibrant outer ring documents its rebirth. But not all ring galaxies form from violence. Some, like Hoag's object, lack clear signs of a recent collision, leaving astronomers to wonder if resonant star orbits could carve out these gaps naturally. In this scenario, gravitational instabilities in the disk might herd stars into specific patterns over billions of years, like sand grains arranging themselves into ripples under gentle waves. It's a slower, more subtle process, one that challenges our assumptions about how quickly galactic structures can self-organize. What makes these rings truly humbling is their rarity. For every 1,000 spirals or ellipticals, there's maybe one Hoag-like object, a reminder that even in a universe teeming with collisions, the perfect bull's-eye requires a perfect alignment of speed, angle, and timing. Spotting one is like stumbling upon a frozen moment in a celestial ballet, where destruction and creation waltz together in perfect harmony. And for astronomers, each new ring galaxy discovered is another clue in unraveling the intricate dance of gravity, chance, and time that shapes everything we see in the night sky. Rising like colossal chimneys from the heart of our galaxy, the Fermi bubbles are one of the Milky Way's most dramatic and mysterious features. These twin lobes of superheated gas stretch 25,000 light-years above and below the galactic center. That's roughly a quarter of the Milky Way's entire diameter. Discovered in 2010 by the Fermi Gamma-Ray Space Telescope, these faint but gargantuan structures glow in high-energy gamma rays, their edges sharp as knife blades against the darkness. Imagine two cosmic hourglasses stacked back to back, each spouting from Sagittarius A, our galaxy's supermassive black hole, like smoke from a pair of celestial smokestacks. What makes these bubbles so puzzling isn't just their size, it's their energy. The gas within them races outward at millions of miles per hour, reaching temperatures of millions of degrees. This isn't gentle stellar wind, it's a full-blown galactic hurricane. The leading theory, a cataclysmic feast by Sagittarius 2 to 4 million years ago, when it last gulped down a massive clump of gas or even an entire star. As material spiraled into the black hole's maw, some of it got funneled into jets that blasted perpendicular to the galaxy's disk, carving out these vast cavities. The shockwaves from that eruption would have reverberated across the Milky Way, compressing gas clouds into stars and potentially even influencing the chemical makeup of our galactic neighborhood. But here's where it gets stranger. The Fermi bubbles aren't just ghosts of a single explosion, they're dynamic, evolving structures. Recent observations reveal they're threaded with intricate filaments of cooler gas, like veins running through cosmic lungs. Some of these filaments emit radio waves, suggesting they're being whipped into shape by magnetic fields or sculpted by the outflow's turbulent energy. Even more surprising, the bubbles seem to have a hard surface, a boundary where the hot gas slams into the surrounding galactic halo with enough force to produce X-rays. It's as if the Milky Way is encased in an invisible bottle and the bubbles are testing its limits. This discovery rewrote our understanding of galactic ecology. Before Fermi, no one suspected our relatively quiet black hole could unleash such violence. The bubbles prove that even dormant monsters like Sagittarius have explosive pasts, and their outbursts can shape galaxies on scales we're only beginning to grasp. Similar structures have been spotted in other galaxies, like the famous radio lobes of Centaurus A, but seeing them in our own backyard drives home their significance. These aren't distant curiosities, they're part of our home's history. Right now, the bubbles are still expanding, their energy dissipating into the halo. In a few million more years, they might fade entirely, leaving only traces in the motions of distant stars and the isotopic makeup of cosmic rays. But for now, they stand as a monument to the Milky Way's hidden ferocity, a reminder that even the most familiar galaxies have tempers, and their quietest black holes can still roar when provoked. Picture the universe's grandest experiment, one where scientists don't just observe galaxies, but grow them from scratch inside supercomputers. Modern simulations like Illustris TNG aren't mere animations. They're virtual universes where billions of particles representing dark matter, gas, and stars evolve over cosmic time under the unrelenting laws of physics. These digital cosmos begin with the smooth soup of the early universe. Then let gravity work its magic, sculpting filaments and voids that mirror the real cosmic web with eerie accuracy. But here's the mind-bending part. They don't just replicate the universe we see, they reveal the hidden processes behind it, like a time lapse of a forest growing from seeds we've never directly observed. The secret sauce lies in the code's complexity. Unlike early simulations that treated galaxies as simple blobs, modern projects like Eagle and Fire too incorporate jaw-dropping details: supernova explosions that blast gas out of galaxies, black holes that heat their surroundings with quasars, even magnetic fields threading through interstellar space. Illustris TNG, one of the most ambitious, simulates a cube of universe nearly 1 billion light-years wide, tracking everything from the birth of individual stars to the cosmic-scale tug-of-war between dark matter and ordinary atoms. The result: virtual galaxies that spin, collide, and age with startling realism, their spirals and bulges emerging naturally from the chaos. Yet for all their sophistication, these simulations still wrestle with cosmic mysteries. Take the diversity of galaxies. Why do some spirals have fluffy, star-filled halos while others wear dark matter like invisible crowns? Current models struggle to replicate the exact mix of galaxy shapes and sizes we observe, especially at the extremes. Dwarf galaxies often appear too dark matter-dominated in simulations compared to their real-world counterparts, while the brightest galaxies sometimes cluster differently than predicted. These mismatches aren't failures, they're clues pointing to gaps in our understanding, perhaps in how stars form, how black holes feed back energy, or even in the nature of dark matter itself. One breakthrough came when simulations revealed the delicate balance required to grow realistic galaxies. Turn up supernova explosions too high, and gas gets blown out entirely, leaving galaxies starved. Turn them down too low, and galaxies overstuff themselves with stars, becoming unrealistically massive. The sweet spot, a Goldilocks scenario where energy from dying stars and black holes precisely regulates star formation, a feedback loop that mirrors the heartbeat of real galaxies. This discovery alone reshaped theories about why galaxies don't burn through their gas too quickly, and why the universe isn't littered with far more stars than we see. The real magic happens when simulations collide with observation. When astronomers spotted quenched galaxies, massive yet devoid of star formation, simulations showed how supermassive black holes could act as cosmic off-switches, their jets heating surrounding gas to prevent cooling. Similarly, simulated galaxy mergers produced tidal tails and ring galaxies nearly identical to Hubble snapshots, proving violent collisions really do reshape galaxies over eons. Yet some puzzles persist, like the too-big-to-fail problem. Why do simulations predict more massive dwarf galaxies orbiting the Milky Way than we actually find? Some theorists suggest dark matter might interact differently than assumed, while others argue our observational censuses are still incomplete. What's next? Next-generation simulations like Millennium TNG aim to model the universe with even finer resolution, capturing the birth of globular clusters and the intricate dance of dark matter substructure. Meanwhile, machine learning is revolutionizing the field, letting researchers explore thousands of slight variations in physics to pinpoint which recipes produce galaxies matching our telescope's views. It's a dance between digital and real, each refinement in simulation revealing new cosmic truths, while every telescope discovery pushes the simulations to greater heights. These virtual universes do more than test theories. They let us witness events too slow or distant to observe directly. Want to watch a galaxy like the Milky Way form over 10 billion years? A simulation can show you. Curious what happens when two supermassive black holes merge at a galaxy's heart. Run the code. In essence, supercomputers have become time machines, peeling back the layers of cosmic history to show us how the faintest dwarf and the grandest spiral alike came to be, one line of code at a time. Galaxies might seem eternal when we gaze at their ancient light, but they too are prisoners of time, destined for futures more alien than anything we can imagine. Picture the universe 10 trillion years from now, long after the last stars have flickered out. The Milky Way and Andromeda will have merged into a single, monstrous elliptical galaxy, Milkomeda, its once vibrant spiral arms scrambled into a smooth, golden haze of aging stars. Nearby galaxies will have either been devoured or flung into the void by cosmic expansion, leaving Milkomeda as a lonely island in an ever-darkening sea. Yet even this titan won't last forever. As the universe expands at an accelerating pace, driven by the mysterious force we call dark energy, the space between galaxies will stretch until every other cluster of stars vanishes beyond an unreachable horizon. Milkomeda will stand alone, its light no longer visible to any other civilization, assuming any still exist. But the real tragedy unfolds inside the galaxy itself. Over unimaginable eons, even stars have lifespans. The longest-lived tiny red dwarfs will finally exhaust their fuel, cooling into inert husks called black dwarfs. Brown dwarfs, those failed stars too small to ignite hydrogen fusion, will fade alongside them. The galaxy's once bright core will dim to a dull glow, its supermassive black hole having swallowed the last wisps of nearby matter. By this point, protons, the building blocks of atoms, may have decayed, dissolving every remaining star and planet into subatomic particles. All that's left will be a diffuse soup of electrons, positrons, and the occasional black hole drifting in the darkness. Yet even this isn't the end. Thanks to quantum mechanics, black holes themselves aren't immortal. They slowly leak energy through Hawking radiation, a process that causes them to evaporate over staggering timescales. A black hole with the mass of our Sun would take 10 to the 67 years, a 1 followed by 67 zeros, to vanish. Milkomeda's central black hole, billions of times heavier, might linger for 10 to the 100 years. When it finally winks out of existence in a faint burst of radiation, the universe will enter its final chapter, the dark era. No stars, no galaxies. Just an endless, featureless expanse where the temperature approaches absolute zero, and the only remaining energy is the faint whisper of particles popping in and out of quantum foam. This seems like the ultimate conclusion, but the universe might have one last surprise. Some theories suggest that the vacuum of space isn't truly stable. Given enough time, a quantum fluctuation could trigger a new Big Bang in a process called vacuum decay. A bubble of true vacuum might erupt somewhere in the void, rewriting the laws of physics as it expands at the speed of light. If that happens, the death of galaxies won't be an ending, just the prelude to a new cosmic cycle, where the story of structure, stars, and life begins anew. Until then, every galaxy we see is like a candle in the wind, burning bright against a darkness that will one day claim them all. Yet in their brief glow, they've crafted a universe rich enough to ask the question, what comes next? From the silent cannibalism of galaxies devouring their neighbors to the cosmic fireworks of quasars illuminating the early universe, we've seen how galaxies are anything but static. They're living, breathing entities in a constant dance of creation and destruction. Remember, the stars in your body were forged in galactic furnaces. The Milky Way is racing toward a collision we'll never witness, and dark matter, that invisible puppeteer, holds entire galaxies together despite being completely undetectable to our eyes. Each of these facts is a thread in the grand tapestry of the cosmos, revealing a universe far stranger and more dynamic than we ever imagined. Now picture this: zoom out from our tiny corner of the Milky Way, past Andromeda's approaching spiral, beyond the local group's 100 galaxies, through the Virgo supercluster's 1,000 more, until all of it, every star, every planet, every black hole, shrinks to a single speck of light in an ocean of darkness. That's the observable universe, containing 2 trillion galaxies, and every single one has a story like those we've explored today. So tell us, which fact bent your mind the most? Was it the ghostly magnetism shaping galactic arms, or the trillion-year fate of fading black holes? Drop your favorites in the comments, and if you're hungry for more cosmic wonders, hit subscribe. Because the universe isn't just out there, it's unfolding, evolving, and waiting for us to keep exploring. Until next time, keep looking up.